Okay, molecular geometry. Last time we did very simple Lewis structures where we used the dots and the dashes, and that's what we're going to be doing, except they're not going to be quite so simple. And we're going to assign what shape they are. But basically, remember we're using dashes or dots to represent the electrons. I will always represent bonds as dashes or lines because I actually think the dots are tedious and I have to draw enough of them. And then we'll represent lone pairs of electrons for the individual atoms with the dots. Okay. The molecular geometry is going to be the 3D shape. So far we're drawing these on paper, which is 2D, right? But in actuality, they're not flat, floating around the world, okay? So we're going to say what their molecular geometry is in a 3D arrangement, okay? And then polarity is something when we're looking at the molecule itself. Molecular polarity is different than bond polarity. Bond polarity is when we look at those electronegativity differences and we say, hey, if it's more than 0.4, then it's a polar covalent. If it's more than 1.7, then it's an ionic. That's not the same thing because you can actually have polar bonds but a nonpolar molecule. Okay, so that's a possibility. And so we're looking at the overall arrangement of that 3D. Basically, we're going to look at it and see, does it look symmetrical all the way around? And if it is symmetrical, then we're going to call it nonpolar. If it's not, then we're going to call it polar. But I will show you how you can actually use that with the bonds. Okay, but for y'all, really and truly, just, hey, it looks symmetrical. That doesn't work for AP, but it would work for y'all. Okay? What governs our shapes is something called Vesper Theory, which stands for, really long stuff, valence shell electron pair repulsion theory, which basically in a nutshell states that the repulsion between sets of valence electrons surrounding an atom cause those to be oriented as far apart as possible. Because we have electron repulsions, because they're both negative, so the structure pushes itself as far apart as it possibly can to minimize those repulsions. Okay? When we're talking about our geometry, we're always going to be looking at the central atom. In other words, what everything is bonded to. And when we're looking at that central atom, we're going to look at how many things are bonded to it and how many lone pairs it has. The lone pairs actually take up more space around that central atom than the bonded pairs because there are two electrons negative out there by themselves not sharing with another atom. Okay, so they're going to repel more strongly than the bonded. When we're looking at a central atom, we're going to look at, I call it areas of electron density. Your paper says electron groups. But it basically means bonded pairs and lone pairs. How many things are around that central atom? And then we're going to use that to look at our shape. So you have this chart. Yours might look a little bit different than that chart, but it's okay. Ours has this one right here. And so if you look at this chart, I want everybody to look at it. And I want you to look at where it says groups of electron groups. Okay? I would say electron density just because that's what we use in AP. Okay? So if I have something that has 4 things around it, if 2 are lone pairs and 2 are bonded pairs, it still has 4 areas of electron density or groups. So I would go to the little 4 section, and then I would say, oh, it has no lone pairs on it, so it's got 4 bonded atoms. It would be tetrahedral. But if it's got 4 areas of electron density and it has 2 lone pairs, what would that shape be? Bent. Okay, so you see how we're using the chart. Helps to know how to use the chart before we start drawing things. Okay? So, let's draw. In your notes, I just want to tell you all this real quick. In your notes, you're going to skip the part that about hybridization and hybrid orbitals. I thought I took it out of your actual paper notes, and I think it got left in. Y'all aren't responsible for that.
So the number of electron groups will always be the same as the number of atoms?
No. No. How about we draw a couple and then see how, yeah, it helps to draw some. So we're going to start with something easy. We're going to start with methane, which is CH4. Okay? And I want to refer to the chart that tells you how to do this, because the first step is going to be figuring out how many total valence electrons. That's how we know when to stop drawing our structure. So carbon is in group 14 and has how many valence electrons? 4. 4 valence electrons. Hydrogen has how many valence electrons? 1. but we have 4 of them. So we're going to need a total of 8 valence electrons in our structure. Okay, so that's how we'll know when we stop drawing electrons. Okay, for simple structures, it's not as critical. For more complicated structures, sometimes that's going to indicate when you should double bond, when you should give lone pairs, when they wouldn't normally. Because most everything is looking for an octet around it, with some exceptions. Here's one of the exceptions right here, which will not get an octet around it. Hydrogen, right. It only has 1 available electron to share. It only has 1 energy level, so it will only have 2, which we call a, well, if 8 is an octet, what do you think 2 is? A duet, yeah. It's a duet, okay? And so now we're going to draw our skeletal structure. Normally, whatever's listed first is going to be your central atom. Carbon's listed first. It's not always the case. If you can't decide what's your central atom, it's going to be the least electronegative, with the exception of hydrogen. Hydrogen will always be a terminal atom. Why can hydrogen not be a central atom? It can only form 1 bond. Right, yeah. So we're going to draw our skeletal structure, and we're going to put 4 excuse me, hydrogens connected to our carbon. And now I'm going to count how many electrons I have available in the structure. How many electrons are present? 8. Because each line is representing how many electrons? 2. Okay, I encourage you when you're counting these, count by 2s. Okay? Some people are going 1, 2, 3. I'm like, just count by 2s, that's faster. It's twice as fast. Okay, now let's look at our chart. We have 4 areas of electron density, or 4 groups around that carbon, and we have 0 lone pairs. So what's our shape? Tetrahedral. Oh, for these that we're drawing in class, I would draw them on the back of this chart just for our practice purposes. Unless you can remember everything I just drew. Or if you have, there's some room in the notes, but not that much, but there's a whole back. And you'll have this with you to like refer to, so you can always refer back to them. Okay? All right, so it's tetrahedral. What's the bond angle? The bond, so this means this bond right here, 109.5. Okay? Now, if I'm looking at that, I'm looking at my carbon-hydrogen bond, and it's actually a nonpolar bond. The difference is right on the edge of 0.4, and most chemists consider the carbon-hydrogen a nonpolar bond. Okay, but what I want to show you is, does it look the same all the way around? Like if I'm looking at a circle, is it the same all the way around? So this would be a symmetrical molecule, so we would say that this is nonpolar, because it does not create any dipoles for the overall molecule. So what we'll be looking at for polarity is, does it create an overall dipole? Is there a slightly positive or a slightly negative end? Okay. In this case, it's the same all the way around, so it would be nonpolar. Okay. And that's going to be important when we get to intermolecular forces next week, because based on the polarity of the molecule is how it behaves when it interacts with other molecules just like it. So that's going to be important coming up next week. I did this all morning. I keep forgetting I want this. All right, so now let's say, sticking with 4 things bonded to it, let's do water. So oxygen has how many valence electrons? Now's where you say 6. Ben's trying to say 6 up here all the time for fun. Okay, and then we have 2 for the hydrogen, right? So again, we need a total of 8 electrons. Okay, so we know we have oxygen, right? And we're going to draw our skeletal structure. So we're going to attach our 2 hydrogen. But I only have 4 electrons here, and I need 4 more. Where's the only place I can put them? Huh? I can't put them on hydrogen. They have to be on oxygen. Okay, so normally you would draw them and you would say, oh, here's a set and here's a set. But we're going to redraw this, because when we go look at our chart, if we have 4 areas of electrons around there, right? Or 4 areas of electron density. We have 2 bonded, 2 lone pairs, but still a total of 4. So go find 4 electron groups with 2 lone pairs and tell me what that shape is. It's bent. So I want you to redraw that when it's bent to be like this, so that you get used to seeing what water looks like. So that is bent. Your chart for bent tells you what is your electron, what's your angle? (109.5). I actually want to tell you that that's not exactly true. It's actually 104.5. So for bent, make that change. Because here's why. The overall structure was tetrahedral. But when I took off those bonds and put lone pairs, these actually take up more space around that central atom, so they kind of push those down a little bit. So it actually ends up being 104.5. Okay, so make that change in your notes. I'm sorry, what? 104.5, because the lone pairs take up more space than the bonded pairs, so it actually, to minimize those repulsive, it kind of shoves those hydrogens down a little bit, which makes the bond angle actually 104.5. Okay. Now, would this be a polar or non-polar molecule? Absolutely polar, yeah, for sure. Because, is it symmetrical all the way around? No. It actually would have an overall dipole of, looks like that. Okay. When we're drawing dipoles, we're showing the bonds. Okay. Oxygen and hydrogen is a polar bond itself, and we draw those dipoles. We can represent it one of 2 ways. Like if I was just showing this bond, I can say, oh, this side is slightly negative, this side is slightly positive. But when we're doing it like this, we tend to show it as a vector arrow, and the vector arrow is going to be, wherever the electron is going to spend most of its time, we draw an arrow towards that with a plus sign on the other side. So oxygen is definitely more electronegative. So we say this would be its vector arrow, would look like that, right? And so if I was doing these over here, then this vector arrow would look like this, and then this one would look like this, which give us this overall vector arrow. That's how we decide. For you guys, really and truly, just look at it. If it looks symmetrical, it's nonpolar. If it doesn't look symmetrical, it is polar. Okay? And anytime you have some lone pairs on the central atom, it's going to be polar. Okay? All right, let's see what we want to do now. Why do you keep doing that? I keep taking that off and said, let's try Bf3 Boron Trifluoride. Yes?
So lone pairs count as groups of electrons.
Mm-hmm. Because it's areas of electron density around that atom. So because they're taking up space, that's why we put them in there. Okay? All right, so we have Bf3. So boron has how many valence electrons? 3. Fluorine? 7, but we have 3 of them. So we're going to need a total of 24 electrons. 21 plus 3 is 24, right? So we're going to draw our skeletal structure, which is going to be boron with 3 fluorines. Boron is an exception to the octet rule that I told you about the other day. It only will have 6 around it because it only has 3 valence electrons to share. But now I need to give fluorine the rest of its 8, because right now each fluorine only has 2 electrons, and it needs how many? 8. Remember, everybody's trying to get to the octet. So to satisfy the octet rule for fluorine, I've got 2. I need to give it how many more? 6. So I'm going to give it 3 sets of lone pairs, right? Count them up. If you count correctly, and if I did it correctly, there should be 24 electrons, right? Count by 2s, starting with the top fluorine. 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24. We're done. Okay? Now, how many areas of electron density is around the central atom? 3. How many lone pairs does the central atom have? 0. So what is that shape according to your chart? Trigonal, I say trigonal planar, trigonal, however you want to say it. Trigonal planar. And what is its bond angle? 120. And is that symmetrical all the way around? Yes, so that would be non-polar, NP for nonpolar. Okay? Are y'all with me so far? All right, it's fixing to be your time to shine, Ryan. Now let's try NH3. How many electrons, valence electrons, does nitrogen have? 5. Hydrogen, I've got 3 of them, so I have 3. So I need 8 electrons. So draw our skeletal structure of 3 hydrogen attached. I only have 6 electrons when I draw it this way. I need 2 more. Where shall I put them? On nitrogen, on the central atom. Okay? So now I have 4 areas of electron density or electron groups, right? I've got 3 hydrogen, 1 lone pair. Okay? So I go find the 4 on my chart, and then I say I've got 1 set of lone pairs. So what is that shape? Trigonal pyramid. Trigonal pyramid and trigonal planar are the ones that kids mix up because they both have 3 things bonded to them. But the difference is one has a lone pair, one doesn't. Okay? So the bond angle here is approximately 107. Oh, it had the 104.5. I see that now on bent. I just now saw that. 104.5, 105. In recent years, they've gotten less picky about the bond angles, and they say approximately now. AP even will accept a range now, and they used to not. They used to have to be exact. Okay? All right. So now we're the answer of polarity. Is this polar or nonpolar? Polar. You see lone pairs on there, it's polar. Okay? Because definitely the overall dipole is going to look like that because you've got lone pairs on that particular atom. Now, next week on Tuesday, we're going to have a lab where we're going to build these in 3D. So it's easier to see them and build them in 3D than it is flat on your paper. And it's really fun because we do it with Play-Doh. So we're like, just like in kindergarten, you get to play with Play-Doh next week. Yeah. No throwing it or eating it. Aw, to the throwing or the eating it?
That's up to you.
Yeah. Okay, let's see. Let's do... Oh, let's do this one. PCl5. So phosphorus and sulfur have the ability to do something called expand their octet. So they can actually get more than 4 bonds, or more than 8 electrons around them. Okay, so we're going to do, based on, figure out the number of valence electrons. Phosphorus, in the same group as nitrogen, how many valence electrons? 5. And then chlorine has how many? 7. But we have 5 of them, so 7 times 5 is 35 plus 5. We're going to need 40 electrons. Okay, so we're going to draw our skeletal structure. So the only thing we can do there is give 1, 2, 3, 4, 5. Chlorine, 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 chlorine. Now, chlorine needs its 8, so give the chlorine. I don't know why that electron was so much bigger. Okay, let's count up the... Oh, forgot some. All right, count them up. Hopefully it's 40. It is 40. Okay, so we're done drawing. Stop putting dots. Okay? So if I have 5 areas of electron density or electron groups and 0 lone pairs, what is my shape? Trigonal bipyramidal. By golly. It says pyramidal. Some of them say pyramid, like on the trigonal pyramid. I usually say pyramidal, but both are okay. And then symmetrical or not symmetrical? Yeah, so it would be nonpolar. All right. Now the last thing I want to do is I want to do one of the I don't know if you have ions. Do you have ions on your paper on the back? The one you're doing is ring that are ions with a charge? Look towards the bottom. I thought there was. No? Okay, well then I won't do an ion. Okay? So then I'll do something that has a double bond. So this will be the last one we do, because the best way for you guys to do it is to practice it. Okay? CO2, carbon dioxide. Carbon has 4 valence electrons. The 2 oxygen will have 12. So I need a total of 16 electrons. Right? So I'm going to start with my carbon, and I'm going to give it its skeletal structure. Okay? So here's what I want to tell you about carbon. With the exception of carbon monoxide, carbon is always going to have 4 bonds. And it very rarely will ever have lone pairs. Again, carbon monoxide is the exception. Okay? So carbon needs 4 bonds. It only has 2 things to bond with it. So the only thing logical for it to do is to double bond with oxygen. Okay? If you remember, carbon, nitrogen, oxygen, and sulfur have the ability to double bond. So does phosphorus. And carbon and nitrogen can actually triple bond. Okay, and you'll need to remember that on your worksheet. Carbon and nitrogen can triple bond. Okay, so now I've got 8 electrons around carbon, but oxygen is missing its 8. So orient them as far apart as possible. I'm going to give the valence electrons to carbon. Now let's go count up and see if I have 16 electrons. Yes. Okay, so 2 areas of electron density. A double bond counts as 1 area because they're there together. So 2 areas of electron density, 0 lone pairs. What is this shape, even if you can't tell obviously what the shape is?
Linear.
Linear. So 180, right? Polar or nonpolar?
Non-polar.
Nonpolar. It's the same all the way around, right? If I were to look at those dipoles, they would look like this, and they cancel each other out, and so that's why it's nonpolar. Okay? Now I'm going to show you this one just in a different color because people always come ask me about this one or something similar. What's that shape? It's only got 2 things. It can only be linear. Yeah. Does it have a bond angle? It's only 2 things. No. Polar or nonpolar? Polar, for sure. Fluorine is the most electronegative. Okay? And then I am going to go ahead and show you an ion so you know how to do it if it shows up at some point. So I lied. This is the next one is the real last one. So we're going to do one of the ions that you have to know for your quiz next week. So what ion is that? Who knows it already? I just gave you the list yesterday. It's phosphate. Okay, it's phosphate. Okay, so phosphate, whenever you see a charge, you have to either add electrons or take away electrons depending on the charge. This is a -3, so what would we do? Add or take? Add. It's got 3 extra electrons. So phosphorus, how many valence electrons? 5. And then for oxygen, we have 24. How did I get those? 6 times 4, right? And then we got to add in the 3 electrons. So we have a total of 32. Thank you. Okay. So we're going to draw our skeletal structure. Then we're going to go and give oxygen its 8. So we need 2 set. I don't. All right, let's count that up and see if there's 32. Who can count by 2s really fast? It is. Okay, so when we're drawing a polyatomic, we're going to put brackets around it, and then we're going to put the charge up here. So we're showing that that whole thing, that PO4, which is covalently bonded, but it has a charge of a -3. Okay, so structure, shape is what? 4 areas of electron density, 0 lone pairs. So what is the shape? Tetrahedral. So same bond angles, 109.5. And then, is this particular thing, is it polar or nonpolar?
I feel like that's a trick question.
It is a trick question. Good job for detecting that that's a trick question. It's an ion. It's not polar or nonpolar. It's an ion because it has that charge right there, -3.
So it's neither.
So it's neither. It's an ion. Ions we don't call polar or nonpolar because they have an outright charge. There's no areas of dipole. It's an outright -3 charge. Okay? Any questions before I end the recording? Okay.
So